All right, let's dive right into this explainer and decode the secret system that guides massive airplanes safely to the ground. You know, if you've ever stared out a passenger window during takeoff or landing, you've probably spotted those massive white numbers painted on the tarmac. To most of us, they just look like completely arbitrary markings, but they're actually part of this highly precise, globally synchronized language. So today, our main focus is exploring exactly how these runway numbers guide pilots. And to really grasp why this matters, we have to start with a wild story about what happens when that guidance system clashes with an invisible force of nature.
Picture this incredibly high-stakes scenario. The year is 1970. A U.S. Navy C-121 aircraft is trying to land at McMurdo Station in Antarctica. Now, the weather is just atrocious. We're talking literally zero visibility. But inside the cockpit, the pilot is actually surprisingly confident. Why? Well, because his instruments are telling him everything is totally fine. His compass is working perfectly, and he's following the exact directional heading given by air traffic control. But minutes tick by, the runway just never appears. ATC actually radios in to tell the pilot he is flying in the completely wrong direction. After multiple failed attempts to find the strip, the plane literally runs out of fuel and is forced into a harrowing emergency landing in a completely random spot on the ice. Miraculously, everyone survived.
So this brings up a really fascinating mystery. Think about it. If the plane's compass wasn't broken and air traffic control gave the correct instructions, why in the world did the plane get lost? How did it just end up flying into nowhere? Well, to solve this puzzle, we first need to understand the absolute fundamental rules of aviation navigation, and that starts with the very design of the runways themselves.
Section 1. The Science of Headwinds. Let's start with the invisible force dictating every single takeoff and landing on Earth: the wind. You see, pilots and airport designers don't fight the wind. They've actually learned to use it, and this perfectly illustrates why. For a massive plane, like an Airbus A380, to lift off, it needs air rushing over its wings at roughly 240 to 295 kilometers per hour. If the air is dead still, those engines have to push the plane down the runway to a ground speed of 240 kilometers per hour. But check out the scenario on the right. If there's a 40 kilometer per hour headwind, meaning the wind is blowing directly at the nose of the plane, well, the plane only needs to accelerate to 200 kilometers per hour on the ground to hit that same 240 kilometers per hour of airspeed. Flying straight into a headwind lowers the required ground speed. This gets the plane airborne much sooner, using way less engine power. And on landing, it means a smoother touchdown, saving the brakes, preventing insane tire wear, and basically keeping all of us passengers safe from violent jolts.
Section 2. Decoding the runway compass.
Because catching a headwind is absolutely crucial for a safe flight, runways aren't just paved randomly wherever there's some open space. They are mathematically perfectly aligned with the Earth's compass based on prevailing local winds. And this brings us right to the core of our explainer. How do runway numbers actually work? So every single runway in the world is assigned a number between 1 and 36. This is not a ranking system. It's a compass heading. A standard compass has 360 degrees, right? Well, aviation just drops the last zero to make it easier to read from the air. So a compass angle of 90 degrees simply becomes runway 9. An angle of 270 degrees, that becomes runway 27.
Let's look at Dubai International Airport as a prime example here. In Dubai, the wind generally blows from only two directions year-round, either the northwest or the southeast. So the runway is built perfectly along that exact line. If a plane is approaching from the desert side at a compass angle of 300 degrees, the pilot looks out the window and sees a giant 30 painted on the tarmac. They're landing on runway 30. But if the wind shifts and the plane has to approach from the opposite direction, say coming in from the Arabian Gulf, the pilot is now flying in at a compass angle of 120 degrees, so it becomes runway 12. It's the exact same strip of concrete, but the number guides the pilot based entirely on their compass orientation.
So the really crucial point here is this simple mathematical cheat code. If you take the large runway number and subtract the small one, it always equals 18. And that 18 represents 180 degrees, a perfectly straight line. Whether you're looking at runway 30 and 12 or runway 27 and 09, the difference is always exactly 18. This brilliant little trick lets pilots instantly mentally map their orientation up in the sky.
But you might be wondering, what happens when the wind is just totally unpredictable? Take a look at this data from Mumbai. Mumbai's geographic location means the wind doesn't play nicely and just blow from two directions. Sometimes it comes from the east, so air traffic control assigns pilots to runway 09. If it blows from the west, they used runway 27. But when the winds shift completely, Mumbai actually utilizes a second set of runways that physically intersect the first ones, runways 14 and 32.
This beautiful Crossing X design guarantees that no matter which way the weather turns, pilots can always be guided safely into a headwind.
Section 3. The Magnetic Drift Twist.
Now, what if I told you that these fixed concrete runway numbers, which remember are tied to the strict mathematics of a compass, actually have to physically change? Seriously, look at Kristiansand Airport in Norway. If you had pulled up a satellite image a decade ago, you would have seen runways 22 and 04. But if you look today, the exact same strip of tarmac is painted with 21 and 03. That wasn't some typo by airport management. The actual compass angles of the runway shifted by a full 10 degrees over a decade. But the concrete obviously didn't move. So what did?
This brings us to the massive plot twist of our explainer. Our planet is not just rock and dirt. It is a giant floating magnet. Deep in the center of the Earth, molten liquid iron is constantly swirling around, generating this massive magnetic field. And because that liquid iron is always sloshing, the magnetic poles of the Earth are not stationary. They are constantly drifting. Right now, the magnetic pole is actively moving away from Canada and racing toward Russia. This means that airports located close to the poles eventually find out their runway numbers no longer match their pilots' compasses. This literally forces them to go out with buckets of paint and physically change the numbers on the tarmac.
Now, here's a fun fact that will completely flip your understanding of a compass. We all know a compass needle points north, right? But remember basic physics? Opposite magnetic poles attract. That means the tip of your compass needle, which is essentially a tiny north-seeking magnet, is actually being physically pulled by Earth's magnetic south pole. So the geographic North Pole up in the Arctic is technically our planet's magnetic south pole. It's a total mind-bending reality of how our planet functions.
And with that, we can finally solve our opening mystery from 1970. That U.S. Navy C-121, it didn't have a broken compass, and ATC definitely didn't make a mistake. The aircraft was flying near Antarctica, which, as we just learned, houses the Earth's true magnetic North Pole. Near the poles, magnetic drift is so extreme and concentrated that over the 6 months just prior to that flight, the magnetic readings had shifted wildly. The Earth's magnetic field had literally moved out from under the plane, causing perfectly functioning instruments to guide the pilots into a vast, empty ice field.
Because magnetic drift happens so incredibly fast near the poles, Canada actually got so tired of constantly repainting their runway numbers that they came up with a clever workaround. They completely abandoned the magnetic compass for runway headings. Instead, they aligned their runways to true north using a fixed GPS system. Since the physical North Pole up by Greenland never moves, the massive benefit is they never have to repaint their runways again. Though it does mean pilots have to completely ditch their trusted magnetic compasses and rely entirely on GPS satellites for landing in those areas.
Section 4. Reading the tarmac markings.
Let's move down to the physical runway itself and see how all this builds into an incredible visual language. Once a pilot follows the compass to the runway, a whole new set of visual markings takes over, providing a vital safety net right outside the cockpit window. Right at the start of the runway, you'll spot these long white stripes known as threshold markings, or piano keys. Now, these aren't just for decoration. They instantly communicate the exact width of the landing strip to an approaching pilot. If there are 4 keys, the runway is a narrow 60 feet. 8 keys mean a standard 100-foot width. And if you see 16 keys, like you would at major international hubs, the pilot immediately knows they have a sprawling 200 feet of width to work with.
Once they're past those keys, the runway basically turns into a giant measuring tape. Sets of 6 smaller stripes let the pilot know exactly when 500 feet, and then 1,000 feet of runway have vanished beneath them. Next, they looked for the aiming point, which is marked by 2 massive solid white blocks. A pilot flying at 300 kilometers per hour locks their eyes right on these blocks because they mark the thickest, strongest part of the concrete, which is specifically designed to take the massive weight of touchdown. And at the far end, a final set of stripes warns the pilot that if the wheels aren't on the ground by this point, they absolutely must abort the landing, pull back on the thrust, and initiate a go-around back into the sky. Because, well, the runway is effectively out of space.
Now imagine trying to do all of this at night. The painted lines are replaced by a brilliantly color-coded countdown. The approach starts with welcoming green lights and standard white lights lining the edges. But as the plane speeds down the tarmac, the last 3,000 feet of centerline lights start alternating red and white. With 2,000 feet left, the white edge lights suddenly turn a cautionary yellow. And in the final 1,000 feet, the centerline turns completely, solidly red. It's this blaring visual warning, dynamically communicating to the pilot that their concrete safe haven is coming to an abrupt end.
But what if the weather is just so bad, foggy, pouring rain, or heavy snow, that the pilot literally can't see the numbers, the painted markings, or even the lights? Well, modern airports use an Instrument Landing System, or ILS. This system uses radio waves to talk directly from the runway to the airplane's computers, bypassing human vision completely. It constantly updates the autopilot on exactly how far off-center the plane is, the perfect glide slope to descend, and precisely when the wheels will kiss the concrete. It guarantees a safe touchdown even if they are flying completely blind.
So, the next time you look out that passenger window and see a giant 32 or a set of painted piano keys, you'll realize the tarmac isn't just a flat piece of road. It's a living, dynamic language speaking directly to the skies. It's constantly adjusting for winds, shifting magnetic poles, and human safety. And honestly, it begs the question, what other hidden systems are silently guiding us through the world every single day, just waiting to be decoded?